The second half of the lecture is a demonstration of using JDBC in an application. And so what I've done is I've taken one of the databases from the textbook, A Guide to SQL. It's the Colonial database, which is a reservation system for a travel company, an adventure tour type company. I've taken the data and I've put it in an Excel spreadsheet so we can kind of look at all of the data. There's a number of issues with this. First off, in the guide table, their primary key is called guide num, and then it's a series of strings. And this is not something that the database management system itself can automatically generate very effectively. This means it would have to be managed somehow by your code, or by an individual. And that's not a good way to do primary keys. As the database system scales up in its use, if the company grows and gets bigger, it's never going to scale. The other thing is databases always maintain an index on a table for searching, and searching strings is a lot more difficult than searching integers. So this is one thing that should be fixed. The table columns have underscores in them, not a big deal, but here we notice on the guide table there's phone num, and then over here on the customer table they call the same thing phone. So that's an issue. The other thing that this Guide to SQL book does a lot is it uses integers, but it wraps them in quotation marks to make them strings. And they did that so they could insert whatever value they want, but there are better ways to do that. That's really not a great way to do it. But effectively, this table structure, we have a guide who will take a tour out on a trip. We have customers who will make reservations and set up tours. We have a list of tour trips they can take. Here are the different trips that they can take. And then we have a many-to-many mapping of which guides can guide which trips. And so not every guide necessarily knows every trip. If we look over here, there are a whole bunch of trips. I think there are 41 trips, and different guides can do different trips. So here we have two different guides who can do the first trip, two different guides who can do the second trip, and so on. Only one guide can do the third trip, but you get the idea. So not every guide can do every trip, but sometimes more than one guide can do the same trip. And then we have a reservation table, and the reservation table says, here's a reservation, here's a trip, the particular tour that we want to take, here's the date it was made, how many people are going, what the price is, other fees, and which customer made that reservation. So this is really the business of the company. The other really four tables are used really just to make reservations primarily. So as I said, there are some issues with this table. So I've refactored this. If you'll look at a few things in this table, season is a repeating group, so that should be factored out. In addition to that, there's also the type of trip. That's another repeating group, and that should also be factored out to normalize this database. There's also, like I said, the primary keys are named oddly. We have ID, num, very, very bad practice. Same column with different names, same data with different names. So what I did was I took the original source data and I've refactored that. We still have the guide, the customer, the trip, and the reservation table, and the many-to-many trip to guide table. I've gotten rid of all the underscores. Personally, they bother me, but a lot of people do them. I've named the phone column the same. So I don't have phone num and phone. I have just phone. Every primary key has been renamed ID. That's important for what we're going to be doing. Also, every primary key is the same data type. They're all integers, which the database management system can very easily assign automatically. Indexing, sorting, very easy to do on integers. So I've basically just numbered these, and then I replaced the guide information in the many-to-many trip to guide table with the correct mapping over here. So the foreign key mapping still matches, but now everything matches as an ID. Every foreign key is the remote table ID. Every primary key is just ID. So the foreign key to the trip table is called trip ID. The foreign key to the customer table is called customer ID. Here on the many-to-many table, again, they had an underscore in it. I just took it out, but a very common naming convention is to name the two tables together as this. So we're mapping the trip to the guide. That's basically what I've done. I've made everything as the primary key to be an integer. I've made sure the columns that hold the same data have the same name. I've made sure every primary key was called ID. And then I also took out the type and the season, and I factored those into their own table. I called the type is a reserved word in SQL, so I called it category. And it has two fields, an ID and then a column called type. And that's hiking, biking, paddling. And this ensures it's easy to add another one without any problem, but also there aren't any spelling mistakes. If somebody types in hiking as a lowercase h and other people type it in as a capital H, or somebody misspells it, that'll be a problem. Same thing with the seasons. By eliminating those repeating groups, we ensure that it's easier to search for early spring or spring or whatever it is that we choose to, and that they will all be the same. So by factoring that out to its own table and eliminating that repeating group, this is a better normalized table. So this is effectively the structure that we're working with. I renamed this database from colonial to provincial. I just went on the thesaurus and looked up words that meant the same as colonial and picked provincial. So once I did that, I had to create my SQL statements to create the table and insert the records. So here's the create table guide. ID for the primary key is an integer, and it has the identity property. It will start at 1 and it will go up by 1. It is a primary key and it cannot be null. And then last name is an invarchar. And invarchar can hold UTF-8 encoded characters, and I kept the same data types as the original table. State is just a 2-character char because we're looking at the United States. Postal code, they made a 5-digit char. That could have been an integer, but char makes just as much sense because you sometimes have leading zeros in certain circumstances. And then this has a higher date, and that's going to be the SQL data type date. Now this is going to play in later, the SQL data type date. There are 2 different date objects in Java. You need to make sure you get the compatible one for the database. With the customer is exactly like the guide, except it does not have a higher date. So everything there is the same. And then the category and season table, really we just are storing a name. And I made those 75 characters just to be safe. But this is where we took out the repeating groups of the type of trip and the season of the trip. The trip itself, again, the primary key is the same. All these fields, the name, start location, state is also a reserved word in SQL, but if you wrap it in these square brackets, it will be treated as a column name, variable name. Have all the other fields, the distance, the maximum size of the party, and then the category and seasons. Category ID is the type of trip it is, hiking, paddling, and then the season ID maps as a foreign key. So we see here, both of those are integers, and they're labeled as foreign key, and it references, in this case, the category table ID column. And that's a mandatory relationship. It cannot be null. Same with the season. Primary key of ID in the season table, and that can also not be null. Reservation table. There's an option here I commented out. You can have on delete cascade or on update cascade. If we update the reservation with certain information, it can cascade through the foreign key. But in this particular case, I just wanted to show you the syntax of that. It doesn't actually apply to this because it's the only thing we're mapping to is the customer. Customers can have multiple reservations, so we probably don't want to delete that because if a customer has more than one reservation, we delete just this entry, that can cause a problem. Here on the trip guide table, we're using the 2 foreign keys together as a primary key. And so here we define trip ID as a foreign key and guide ID as a foreign key. And then we say the primary key is a composite key of these two together. Now to go to insert the data, this is all the same data that was in the provincial or in the colonial database from the Guide to SQL book. But I've updated with the correct foreign keys and updated the primary keys. SQL Server and other systems have a command you can do. This is the command that I'm using here. Set identity insert on the guide table to on. And this allows me to override the identity property here on each of these. So this allows me to say, I know you would normally assign this SQL Server, but I want to assign it this time. And so by setting this property to on, I can now say, this is your primary key. And the only time you'd normally ever want to do that's when you're preceding a database like this, where I'm preceding and I've already worked out the foreign key relationships. Now to do that, you have to specify the columns in order. Normally if you do an insert statement, you can just provide a list of values. But when you're providing the primary key, you have to provide the list of the columns in order to include that ID, because that's normally not a column you're allowed to insert. But otherwise, set that property to on, insert my records, and then as soon as I'm done inserting the records, I turn that off. And by turning that off, that allows the identity property of that tag to automatically assign the next available integer. And so just do that for all the tables. There's all the data that was in that table that I showed you in each of those tables. So here's all the data out of the database. And what I've also done, I didn't show you earlier, I found this little trick on Stack Overflow, how to drop a list of SQL Server tables but ignoring constraints. Normally once you put those foreign key constraints in there, you cannot delete a table if it has an active record that has a foreign key to another table, because that would orphan the other one. So here's a little jewel off of Stack Overflow that will basically go into a table, and each table in the database, and it will drop all of the constraints. So it basically undoes all of those foreign key requirements. So what I do here is drop all the foreign key constraints. It actually drops all constraints, but the ones I'm concerned about are foreign key constraints. And I say drop table if exist, and I get it. So this says if the table's there, go ahead and drop it. And then I'll recreate it. This is going to come into play later on. These lines up here will come into play later on when we're doing our unit testing. We'll talk about that in a second. Now, if we look at our data structure, we have a guide, a customer, we have a type of trip, a season for the trip, we have the trip itself, and we have the reservation. And then we map what guides can do what trips. So in our application, now don't panic too much when you see this. We're going to have a customer, a guide, a season, a category, the type of trip, and a reservation. All of those are going to inherit from entity base. Entity base has the primary key property, so we'll go look at the source code for this. Entity base is the base class of all the objects in our application, and it's going to give us an ID field that acts as the primary key in the database, and the corresponding getters and setters to this. It also provides a compare to for, it says here, sorting on the primary key. But because every single entity in this application, every single class has an ID field, you need to be extremely careful comparing. Make sure you compare instances of the same object type. Otherwise, you might get a false positive on that. This is an abstract class because we're not going to make an instance just of entity base. But this is going to be the base class of all of our applications. And it's going to implement comparable with the object. So it has a private field ID that's going to represent the primary key in the database. And then this is something you may not have seen before. The setter for the ID field protected, so an application outside the package cannot use it. Basically, by being protected, this is normally assigned by the database system. So we don't want somebody to just arbitrarily be able to set the ID. We only want things within our own package to set the ID. It's returning an instance of itself, and that's very important. It is returning an instance of itself. And this means that we can daisy chain the set ID call onto a constructor. We'll see an example of that later on. This is something normally setters return void, but by being able to do this, we could call a constructor or call any other method and then daisy chain the set ID call along with that. I'll show you where that's important later. Near the compare to, we simply compare the ID field. So as an example, if we look at our customer object is going to extend entity base, which means it has an ID field in it automatically. And we have a last name, first name, address, city, state, postal code, and phone. All of these are fields in the customer table. So we have ID, which we got from entity base, last name, first name, address, city, state, postal code, and phone. We duplicated those fields in our class. And all of those should be private. Not sure why I didn't do that. Those should all be private. So they're all private now, like they always should have been, like it never even happened. We've got our default constructor and our overloaded constructor. Our overloaded constructor takes all of the parameters except ID, because again, ID should be set by the database system. And so we assume those. We have all of our getters, and then we have all of our setters. And each setter will return the instance after the value is set. That's a approach that's starting to become a little more common again with setters in Java, which I showed you earlier on the entity base. That way, again, we can daisy chain calls to the setters, and it will work. This is based somewhat on the builder pattern implements this approach for design patterns. So, all right, so there are the setters. And then I have a toString, which is going to display this customer. And that's pretty much how every one of those objects should look. Every one of those objects should essentially have the fields that match the columns. So the class should have fields that match the columns. The data types should be a compatible match. They should all inherit from entity base. And that gives them the ID field. And that way, all of our stuff will have entity base, and it will all have the other information that we need. Now, this application uses something called the repository design pattern. The repository design pattern is a common approach. It's used a lot with ASP.NET and C#. It's somewhat used in the Java field, in the Java area, but not as much as it is in the C# area. It's an approach that follows separation of concerns very well, and this is part of why we see so many different objects in here. But you'll see them in a second here. Why? So the customer object, the guide object, the season, category, trip, and reservation, all of these represent the objects necessary for this application to function, to make a reservation, to add a new customer, to set up a new trip, to update a trip. All of that is represented in those objects. And the business logic is handled there. However, we also have a separate issue, which is our persistent storage and retrieval of those objects to and from the database. And so to maintain separation of concerns, we're going to create a separate object for each of those called a repository. And that repository object is going to handle all of our persistent storage operations. And it's going to be separate from the business logic in our main objects. So it's a very important design pattern. And so it's going to start with an interface. And so the interface that I've created for this, I've called repository. And this is going to simply define the API for all of our repository objects. This will be the way that we interact with our database, this set of method calls that are defined in this interface. The advantage of doing a repository, there's several. First off, we get separation of concerns. We don't have to mix and match database operations with our business logic directly in the class. So by separating this into another class, we automatically have separation of concerns. We have our focus of database operations in our repository. We have focus of our business logic in our main application. Each main application class will have a corresponding repository instance with it that does the database operations. By everything following an interface, we guarantee that the same API calls will be available on every one of our business objects, our business class objects. And because a lot of this is going to be repeated, we can implement a lot of it in a base class so that we don't have to implement the same thing multiple times. So let's go take a look at, first off, the repository. What will be our API call? We're going to have a count method, how many records are there? A get record that will look up something on its ID. Get first, which will return the first instance in the database. You have a collection, get all. And this can be anything that implements the collection interface. It could be an array list, a set, a map, anything that implements the collection interface. Get all will return all records. Get page. Paging is something that when you have a large set of data is very important. If you think of Google, with Google, you do a search and then you have 10 records, but it might say found 44,000 records in 0.02 seconds. And so you have 10 records, and if you click the next page, that shows you the links that found 10 through 20 and so on. That's paging. And so what we have here is what page number do we want to start with and how big do we want the page to be. And so this allows us to get part of our records at a time. Get, collection, and search are basically just going to allow us to pass raw SQL statements in. And search is going to take a where clause. But the get, collection, both of those will allow us to simply pass in a string in order to build out some custom search. Add, update, and delete. We'll take an entity and it will insert it to the database, update it, or remove it from the database. And then we have add collection, update collection, delete collection. This defines a Java API to fully interact with our database, working with individual instances, individual records, and collections of records. The nice thing about this is there's nothing in this that's really specific to whatever database management system we're using. So by using a repository, not only do we get separation of concerns with being able to have our CRUD operations in a repository and having our business logic in our main classes, we also now have abstracted away the actual database implementation. So now if we wanted to switch from, say, SQL Server to MySQL, or from MySQL to PostgreSQL, or from Oracle to SQL Server, or whatever, we can do this in our repository base class and our repository objects and not worry at all about interfering with the business logic of our application classes. So let's go look at the base class for repository. Now notice, this is an interface, but it's a generic interface, and it says this is tied to a data type that extends entity base. So this repository can only work on something that has an ID property. And so ID is the primary key of all of our tables. So repository requires that every table have an ID property. So our base class, repo base, is going to implement the common API methods that don't require something unique about their class type. It's a generic, and it must be typed with a class that inherits from entity base. Repo base implements count, add collection, update collection, delete collection, get and set schema, get and set table. And so we have our import statements out of the Java SQL namespace, which comes from the JDBC library. It's an abstract class. And again, it is a generic type as long as that type extends entity base. We have our connection. Our connection is going to call our JDBC utilities class get connection method. Now, if we look up here at JDBC utilities, this is just a utility class to give us a JDBC connection, nothing else. So it has a static get connection method that's going to return a connection instance. And it takes here a connection string. So that string is a static string, and that's the connection string to my database I'm using as the example here, the provincial database on localhost, and I'm using the SA account with the password. Super secure. Obviously that's not the normal password I use. The connection, the get connection method, I'm going to try to build the instance of the connection by calling driver manager get connection with that connection string. If there's an error in here, this will throw an exception. You have to catch that exception. I'm going to reset the con instance to null, print the stack trace. You can do other things with that exception. You could get the error code, unwind the nested exception, so on. And then finally, I'm going to return an instance of the connection object based on that. So this allows everything in my application to get a connection, and I only have to implement that once. So my connection object, I'm going to call that static get connection method to get that back. I have a schema and table, and what we're going to do then is anything that actually implements this will set the schema and table. At this point, remember this is an abstract class, so these will be set later on. And these are public so that the other things that inherit from it will be able to work with these directly. My count method, I say select count star from get schema plus get table. So I just literally build a string, and it's going to call get schema get table to build out the full string. And then I create a statement and a result set instance. I set a count, and then I do a try catch, because if there's a problem with any of this, it will throw the exception, and I want to be able to deal with that exception. So I create my statement from my connection object. I get a result set back by executing that query. Move to the first record. Should only be one record, but you still have to move to it. And I say if the result set is not null, then I'm going to get an integer of the first column. There's only one column in the result set, but I'm going to go ahead and get it there. And that will be the value of my count as an integer. And then assuming all went well, I'll return that count. This will work for any object type because each of them will have their own schema and table. Get first, get all, get page, get collection, add, update, delete. None of those can be implemented here because they all require specific data. However, I want to make sure they're all defined there as abstract classes. Now the add collection, update collection, and delete collection are all going to loop over the collection provided as a parameter. And when they loop over the collection provided as a parameter, they're going to call the individual add method. And the add method returns true or false if it was successful or not successful. And then I add up the number of elements processed, and then I return a number. Now, what I've done here is I've taken the list size and I've subtracted how many elements processed. Now, if everything works correctly, that should be 0, but in case there's any issue with that, I'll do the absolute value of that and return that. So that would basically return an error code of how many records were not processed. Now the update collection does the same thing. It loops through every element and just calls individually the update method. then the delete collection does the same thing. Now the add, update, and delete individual methods are not implemented, but they are defined as abstract. So anything that inherits from this will eventually need to implement them. So because we can rely on that, we can call this here. So this gives me the ability to implement these methods in one place and then not have to worry about setting them up later. Here's the get schema method. We just simply return what the schema string is. On the set schema, what I've done here is something kind of important. Normally, the way these are defined, if we actually look over here at the table, like the default schema in SQL Server is DBO, database object. See DBO dot and then the table name. The DBO dot table name. So what we've done here is when the schema comes in, I'm going to look at the last character and say, is the last character a dot? If it's not a period, we're going to add that. And that way, whenever we go up here, like to the count method, whenever we go up here and say get schema plus get table, it would say like DBO dot category or DBO dot reservation. And that builds the SQL syntax out correctly. And then we have our get table and set table methods as well. So those are the things that are common to all of our repositories. Now, let's look at a specific implementation of the customer repository. The customer repository is going to manage the CRUD operations for customer objects. It doesn't do any of the business logic. It only does the CRUD operations to and from our database. So that's create, read, update, and delete. So the customer repo extends repo base and is typed to a customer object. Customer is going to inherit by extending repo base to the customer. Customer itself extends entity base, so this will work. So what we see here is we bring in the different items we need from the JDBC library. Say here, customer repo extends repo base tied to a customer object. So we're inheriting from repo base. And we implement the repository interface for the customer object. So our default constructor, we're going to call set schema and set table. And so set schema, we say DBO, set table is customer. Every repository needs to do this in its constructor. Then we have the get on the ID field. We're going to look up a record in the database based on its primary key. By all the primary keys being integers and all of them being called ID, this works very smoothly. So all of these lookup operations follow the same basic structure. We have a statement, a result set, and then we have a customer instance here that we've created. We've used the default constructor. Our syntax, select star from schema table where the ID equals the ID. I didn't put a space here. There's no space between the ID and equals. SQL does not like that, even though we normally do that in Java. SQL doesn't like having a space there. We create a statement from our connection. Our result set, we're going to execute this query. So what this would end up being is select star from DBO dot customer where ID equals whatever this parameter was, 5 or whatever, and then the semicolon. This is the exact syntax you would put in over here in SQL Server Management Studio or whatever other utility you're using to work with your relational database. And then we go and get that out of the database as a result set. So we say, if that result set is not null, why would it be null? If that ID did not exist in the database, then this would be null. So we say, if the result set is not null, move to that record, and then we're going to say customer set ID, and we take that ID parameter, and then we set the last name. This is the setter method in our customer object, and we give it the value of our result set, get a string, with the column name, last name. So here's our result set. We're going to get the column called last name. Its value is what will be the parameter to set last name on our customer object. And that's all we do for each of these. We just call the setter methods, and as the parameter, we use the result set get methods to get the particular column that matches to that. And this will give us a customer object with the entire state set up with every field set to the value of the database, and then we return it. If there was any problems, we catch the exception and then return null. Get first, we just say select top one. Now top one is SQL Server specific. If you wanted to implement this in a different manner, what you would probably do, like in MySQL, it's limit one. You have to look up whatever the particular syntax is of your particular database system. But they all have some syntax along these lines. And this is based on the primary key. So it selects the element based on the primary key. And we do the same exact thing that we did before, exact same syntax here. That could actually probably be factored out, refactored into a private method and reduce some code there in this. But here we do the get page, and this is a SQL Server specific set of syntax. Different database systems will do this. We have the offset and fetch page size. And so the offset and fetch are, again, SQL Server specific, but this does paging. This was introduced, I think, in SQL Server 2012. So you'd have to use at least that version or newer. The getAll method is going to just keep building on the same process, except now we're going to work with a list. So remember, the getAll is going to return something that implements the collections interface. And so in my case, I chose an array list. I could have used a set. Since every record has a primary key that's unique, a set would have been a good approach as well. I just chose an array list. Now, they say it's not a safe call on a very large record set. And so if you're something like Amazon, with Amazon's product list, or eBay with all the things that they have for sale there, this would return too much data and it would crash your application. So if you're dealing with an application that has a really large set of data, you'd want to take this out of the interface, and you would want to take this out of your implementation. But on an application like what we're looking at, relatively small, pretty straightforward to do it, no big deal. But on a large database with a large set of data, this is probably not something that you'd want to do. So the basic structure here, we create a list of customers and our statement and result set. And what we're going to do here is say select star from schema table. I would say select star from dbo.customer. And we're going to go and run that. That should give us every record in the database for that table. And so we're going to loop over every record and say while there is a next record. And we call it list add. Now what this is doing is a little tricky here. We're calling the constructor. We're making an anonymous customer object directly inside of the list. So we call our customer constructor, new customer. We look over here at the customer constructor. It takes last name, first name, address, city, state, zip, and phone number. And so we're going to pass the constructor last name from the result set, first name from the result set, address, city, postal code, and phone number from the result set. But we also need to set the primary key. Now, normally, we wouldn't set that. That's provided by the database. And so our constructor doesn't allow us to set the primary key. But remember, the set ID does return the instance of our object. And so this is what I was talking about. We can daisy chain this. So here's the end of our customer constructor call. We've daisy chained the call set ID on that. Not sure what just happened there. We've daisy chained the call to set ID, and we passed in the result set get integer ID on that. So that gives us a new customer object. I had to cast it as a customer object here because probably something to do with the inheritance of entity base, I would assume, but I had to cast it as a customer object here, even though I'm calling the customer constructor. So I call the customer constructor, get all the fields in the customer constructor, set the primary key there as well. So now I have a customer instance right out of the database with every field set, and then I add that to the list. And I do that as long as there are records coming to me from the result set. So this will basically build a list that maps every single object in the database, every record in the database. And then when I'm done, I'll return a list. If there are none, then it will return an empty array list. But if there are records, it will return every instance of that record set. Now the add just builds an insert statement. Now this is a little bit different here. The insert statement, we're going to just build out the syntax to actually insert a new record into the database. And so you'll notice we say insert into, and then we provide the columns in the specific order and then the values using the getters on our object. So we're building a string that would represent the syntax we would actually type into a screen here. Insert into, and all the rest of it. And so we build that out. Now again, notice we're not setting the ID property. That is set by the identity property in the database system itself. We go over here and say identity 11. That's what sets the primary key by the database management system. It's very important the DBMS does this and not us, because the DBMS has the one accurate picture of the data. We don't know if someone else is coming behind us and doing inserts as well. There's no way for us to know what a valid identity value would be, but the DBMS does. So we insert all of the column values except for identity. And we're going to use a prepared statement because we want to get those generated primary keys back. So we use the prepared statement and we run the SQL and we say return the generated keys. And then on the statement, there's really nothing that comes back except, one row inserted or one record updated. So there's no real result set, but what we say here is get generated keys. Now I've only inserted one record, so there's only one key in this statement. We get a result set, we move to that first record and say get the integer at column 1, and that is our primary key. Because this is an object reference, we can update the primary key here. And this is why we don't have the ID as a field in the constructor. This is why we have to do it this way. So we get the primary key back from the database and then update the state of our object there. And at this point it all worked, so we return true and we're good. Otherwise, if something failed in here, if we did not insert the thing correctly, we would return false. And so that's how we go about adding a customer. Update is the same thing. Basically, we build a string that would update each of the fields using the getters on our customer instance. This has the latest values of the fields from our application. So this would be the business logic of everything. We build the string for the update sequence where ID equals the value there. Sorry, let me get down here back to the update. So we say where ID equals customer get ID, and then we just simply execute that SQL. Now again, we're not getting a result set back because there's nothing to get back when you do an update. It just says one record updated. If everything works here, we return true, and we're good to go. The record was updated. If there was a problem executing the statement, we'd catch the exception. In that case, we would return false. Delete, we simply build the delete string and use the where ID statement so that we get the one record. We delete that. Again, no record there. I was printing this as a debug statement. There's no result set to get back, so we simply return true and we're good. If there was a problem, it will return false. The next two methods in the repository work together in order to enable you to dynamically search for instances for records in the database. And so the first one is this get collection method. And the get collection method takes an entire string of SQL. And so you have the full select statement from the SQL. And essentially it works just like the others. It will execute the query, get a result set back, and then create instances of Java objects based on the fields from every record that's returned based on that. The next method, though, the last method, is search. And the search method does a SQL lookup where you simply provide the where clause. And really that's what we care about since we're working with individual tables. In the case of the where clause, we provide that and it builds the full select statement and then calls get collection. Now, where this might come into play, where you could almost even make get collection private if it wasn't required in the interface. But if you were going to do a join and have a single instance where it showed data across multiple tables, you would create an instance of an object. You would create a class, that we would generally call a view model. A view model is used to display data that's joined across multiple tables. And it's used only for display. It's not part of the business logic. Used a lot with ASP.NET, and we'll cover that in a later class. But essentially, though, the view model object would not be used for business logic the way that our classes are. It's only used for display. So the get collection, you could actually implement that with a view model if you wanted to combine data. But normally though, we're just simply combining these two together. So we build dynamically the full select. Truth of the matter is we could really probably combine these into just the search, but that's that. So at this point we've effectively covered entity base, the instance of our object as it relates to the table. We talked about the customer, how it has all the same fields as the columns in the database table. We talked about the repository interface to define our API to do all of our CRUD operations. We talked about putting code in the base class so that we don't have to repeat ourselves. We talked about the JDBC utilities to get an instance of our connection. And then we talked about the repository implementation itself. And so again, if we go back to BlueJ, we have a repository that will provide the CRUD operations for the database for our customer business object. And so what we see in this, in essence, is that, drag this over here where it's a little easier to see. Our customer does all of our business logic. Our customer repository does all of our read and write and lookup to and from the database for our customer objects. We get that separation of concerns. How do we actually work with this, though? What I've done is I've created a set of unit tests. And so the unit tests demonstrate pretty thoroughly, I think, how to do all of the operations. So there are a number of libraries that we're importing. So we're going to import all the JUnit libraries. And then I've got some libraries here for reading from a file on the file system. I've got an array list in order to deal with collections. So again, the array list is so that we can deal with the parts of the repository that return collections. And then we've got our components out of JDBC. So the customer repository test, what we're going to do is there are a couple of things that we're going to take advantage of here. We've got the constructor, and then down at the bottom of the code, these are built automatically as part of this. We've got a setup and a teardown test fixture. The setup will run before every test, and the teardown is called after every test. And so what I've done is I've written a reset database method. Part of the thing, one of the guiding principles of unit tests is each unit test should stand alone by itself, independent of any other test. You cannot rely on one test having ran before you run another test. Every test should be able to be run individually. And so the reset database method will run the SQL commands to destroy the tables, recreate them, and reseed them with the original data. What this will effectively do is it will ensure that for every single test, every database call is dealing with the exact same set of data, no matter what. If it doesn't matter if it's the only test running or if a bunch of other tests have ran before or after it. Before and after every test, it ensures the database in the exact same condition. So in BlueJ, I've made a subfolder data, and I've created a file seeddata.txt. And seeddata.txt is this file. And so what it will do is it will remove all of the constraints from the database. It will drop the tables if they exist, and then it will create all of the tables. And then after it creates all the tables, it will insert the data with the given ID that we've already preset. And so it inserts all of the data into the database every single time, so that for every test, oops, didn't mean to do that. For every test, the database will be reset to the exact same known good state. All I do is just read that file line by line, put it into a string builder, and then call toString. So that string now has every single command that we just looked at in that text file. And then here I was printing it as I was debugging and testing with this. We don't need that printed. Then I create a statement, I run that statement, and then close the statement. So this will effectively, we talked earlier, we don't get a result setback, but essentially a statement can run any data definition language or any data manipulation language command. In this case, we're running both. We're running data definition commands to remove constraints, delete the tables, create tables, and then the data manipulation commands to insert records. And so we can get an IO exception if the file isn't working, so we couldn't read the file. Or we could get a SQL exception if we can't get a connection and can't talk to it. So we catch both of those. But assuming everything ran, each time this runs, it will read that file, take all those SQL commands, run them, and when we run them, that will reset the database on every single unit test to a known good state. So we run it on setup and on teardown. Setup is necessary to make sure the database is set up for each test before the test starts. So if it wasn't set up initially, the first test, it will make sure it's in good shape. If a test fails, it might not run teardown. So also on any subsequent tests, we'll run reset to make sure that the database is in good shape. Assuming a test works though, we reset it again so that it's ready for the next test or ready for our application to run with our sample database. A lot of times it's a good idea to actually have your test database be separate from your development, definitely separate from your production database. It should always be separate from your production database, but in this case we're developing against and testing against the same database. So we run this twice, even though it's a little bit redundant. It's in case a test fails, or in case it's the very first test, we want to make sure it's in a known good state. So those run automatically before and after every test. Our count, we just basically run through the entire repository API. The count test, we're going to make sure the customer count is greater than 0. You know, basically, if it's counting anything, we want to make sure that it's got a number there. And in this case, again, this is where I was testing to make sure that that worked. So all of our unit tests are written in this AAA format. We arrange, set up, we're going to do an action, and then assert if the action worked successfully. So we create a new customer repository interface here, and then we call cr.count. So we're calling one of the methods in our repository, and we get back, in this case, the number, how many records are there, and then we make sure that's a number greater than 0. So we arrange, act, assert. All of our unit tests should be written like that. And in this case, if there was an exception with the customer repository, I'm going to automatically fail if the message couldn't count records. The get test I'm going to arrange by creating a customer repository. I'm going to act by getting the first customer. In this case, the first customer, the customer ID is number 101, and that came from our seed data. So we'll get a customer instance back from that get method, and then we say, okay, we want to make sure that's not null, first customer, because if this fails, it returns null. So you can see here, to actually work with our database programmatically using the repository object, I don't have to write any SQL at all. I just make Java calls, and the repository under the hood hides that SQL. Now here on the get first test, in the case of the customer, what I should have is, again, looking and knowing my seed data. I get customer 101, and then I'm going to get first. 101, the customer ID 101, should be my first customer. In fact, if we go look at the record on the customer, 101 is Liam Northford. And so when we get first, that sorts on the primary key. That record is my first customer. So what I'm doing here is I'm getting the same customer twice. First customer, top result customer, and they should be the same. So what I'm doing here is I'm saying is first customer compared to top result customer. The compare to should return 0 because they're equal. The IDs are equal. So we're saying, does compare to return 0? If it does, then they are equal. The get all test, what I'm going to do is call customer repository get all, and I want to make sure that the list that's returned by get all has a size that's equal to the count, because the count is how many records are there. So get all should return all of those records. So again, I arrange by creating an instance of the repository. I act by calling a method on the repository. And then I assert that it did what I expected it to do. But if you notice, working with the database, I am not writing a single line of SQL. I am just working with a public API. On the get page test, what I've done here is call the customer repository get page. I want to get the first page, and the page should have 3 records in it. And so the first page, I just want it to be 3 records long. And then I check the size of my list. Is the size 3 elements long? Now on the search test is actually going to use get collection. So I can work that. So in this case I say, I want to search where city is like London. And I'm using the like syntax here of the SQL. And so this should return 0 or more records where the city field has a value like that. And so in this case, I happen to know from my seed data that the customer, in this case Liam, has a city, Londonderry. And it looks like another person also lives in Londonderry. So there should in fact be, based on my seed data, 2 records. So I just want to make sure the list has a non-zero number of records. So in this case, if that like matched, then I should have, in fact, size should return 2. 2 is greater than 0, so that should assert to true. The add customer, what I have to do is create an instance of a customer and then call add on the customer repository. Just customer repository add, I pass it a customer object. Now that add will then set the ID property for me. So notice, I never set the ID property because I don't know what the database management system's going to do. It will give it whatever the next available number is, but I don't know what that number is. So I just pass it an instance of customer, it'll put it in the database, and then assign whatever the primary key is that came back. So if the add was successful, the add returns a Boolean, and it should be true if it was successful. So I assert that the add worked, that was true. The customer update customer test, what I do here is get first. I'm going to change the last name. I call the setter method, set the last name to some weird string, and then I'm going to call the customer repository update and pass it that customer object where a field has been changed. Now, I've called get first, I've modified it, I've updated get first in the database. And now I'm going to act by getting first again. I want to get it again out of the database. This update should have written the record to the database. Now when I get it back, it should have a new last name. So when I get it back, customer get last name should equal that weird string. And if it does, that will be true. Here's another one where I'm going to do a delete. Now the delete, this is a little tricky because foreign key constraints in the database will control what order you need to delete things in. If there are foreign keys that cannot be null, you have to delete things in a very particular order. So very quickly I'll show you. If I wanted to delete a guide, I would have to go delete the trip guide records where the guide ID matched my guide. I would have to delete those. And then I could delete the guide. But I can't delete a guide as long as there's a record over here that's a foreign key. If I have a trip that I want to delete, I can't delete the trip until the reservation, all the reservations that use that trip are also deleted. I can't delete a reservation till the customer is also deleted. I can't delete the customer until, the trip. I can't delete a trip till the trip guide relationship is deleted. So there's a very particular order that you would have to delete these things in if you were wanting to do a cascade delete. So there's a couple of approaches to that. I showed you in the earlier example where you could say on delete cascade. You could add that syntax into the create table statement. But to get it to work with the repository, you would have to go and find the relationships in the order, find the first one that doesn't have a foreign key relationship, delete it, then follow the foreign keys out to delete all the records. It can be a little tricky. So just to test this, what I've done is I've added a new customer. And so the new customer has no foreign key relationship anywhere. And then I'm going to get the ID from the new customer. What did the database assign as the primary key? And then I'm going to delete that customer. And then I'm going to go try to get it again. Now if the delete was successful, which since there's no foreign key on any other table, this delete should be successful. When I go to get it back out of the database, it shouldn't be there. It should be null. And that's what I assert. Is it null when I go look it up? It was valid when I inserted it, but after deleting it, it's no longer valid. So literally, I'm just putting a record in, deleting it, and making sure that the delete was successful. And that avoids any foreign key constraints. Otherwise, your delete test might fail. And that's all the test. I basically have tested all of the stuff in the database there. I've tested the whole repository, the search, which also covered get collection, all of the gets, the add, update, and delete. Now, I don't need to do the add collection, update collection, delete collection, because under the hood, those really just call the individual add, update, and delete. So if those work, then the add, update, delete collection will also work. So that's, in a nutshell, an example of how to use the repository. You'll notice I'm not writing any SQL. I'm just using, it abstracts away, it hides the underlying database. If I ever wanted to redo the database and put it on a different system, all I would have to do is update my repository, my repo base, and my individual repo objects. My business logic would never, ever be in danger. So for the assignment, what I want you to do is I've provided 3 examples of repositories. I provided a customer repository, a guide repository, and a season repository. What I want you to do is to write your own repository and test for the category, the trip, and the reservation. And then I provided an application. And the application hold on here and I'll show you the application. So the application is a simple reservation application for the provincial reservation system. I've got a scanner to get input from the keyboard, and I've got an array list so that I can deal with collections. Now, so far what I've done is I've created an example guide repository, customer repository, and season repository. You're going to need to create the other repository instances, and you'll add instances of them here for our other three object types: the trip, the trip type, the category, and the reservation. So you'll need to create those reservations. Then I've got the scanner here. And so in the main method, I simply provide a basic welcome message. And in a do while loop, I provide a basic menu. 1, 2, 3, 4, 5. List information, add a new trip, reservation, guide, or customer, update a trip, reservation, guide, or customer, and then remove a trip, reservation, or guide. We would never delete customers because we want to be able to reach out to them in the future. Even if they haven't been anywhere with us for a while, we still want to be able to reach out to them and try to get them to come back. So you would never, ever in a real system delete a customer and then exit. So we do the try catch. And the reason I have this on a try catch is I want to get a next int, but if a user types something weird that's not an integer, that'll throw an exception. And so we print out a message, and then we'll switch on the menu. And so if they chose 1, we'll call list information, 2, add information, 3, update information, 4, remove information. List information, we would say we want information about trips, reservations, guides, customers. The only thing I actually have implemented right now are guides and customers. Enter your selection, and so again, you'll want to add the information for trips and reservations there as you do this. Guides, if I want to get information about the guides, I'm going to call get all the guides. I'm just going to loop through all the guides, and for each guide, I'm just going to print the guide. So I'm going to call toString right there. So that'll just print the guides. For the customers, same thing. I'm just going to go through and just print all the customers. And so that will show me the information about the guides and the customers. Add information, just follow that basic pattern. And I want you to go through and add information. You'll have to prompt for last name, first name, address, city, state, postal code, phone number. Update information, you'll have to provide, prompt and scan that information. Remove information, same thing. Now, removing is going to be the most challenging because, as I said, you're going to have to be very careful about the order in which you delete items. You may need, on the remove information, if you want to remove a customer, you might have to remove a reservation first. You're not going to remove a customer, I'm sorry, but if you remove a guide, you'll have to remove the trip guide many-to-many mapping, and you'll have to remove the information that corresponds to foreign keys. So removing is going to be challenging, but basically what I want you to do for this application is I want you to write a repository for these 3 items, and you can use these as examples. Write unit tests for your repository that work with these 3 items, and finish the application. And at that point, you will have an entire information system based on that 3-factored colonial database out of the Guide to SQL book. And that's that. Let me know if you have questions.